Okay, let's do this, you guys. Unit 3, summarizing quantitative data, whereabouts. Okay. Do you do this? No? Okay, range and interquartile range. Both measure the spread in a data set. Looking at spread, let's see how much data varies. Range is a quick way to get an idea of spread. Takes longer to find IQR, but it sometimes gives us more useful information about spread. The range Ron recorded the daily higher temperatures for two different cities in a recent week in degrees Celsius. The temperatures for each city are shown below. Kansas City. What does that mean? Is that some kind of fucking zip code or zip code? I don't know. Got a fucking. Anyways, 23, 25. Okay. Calculate the range of the temperatures in Kansas City. More. This one. So, yep. So what do we got? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4. We got this 3, we got 25, 33. So we got 33 minus 25. That's 8. No? Are you for real? The range, temperature, the range. It's not the interquartile. The range is the highest, which is 35 minus 23. 35 minus 23 is 12. 12. Okay. Calculate the range of temperatures in Paradise, MI. We got 28 minus 16. Minus 16. That's 12 also. That's 12. What is the best interpretation of the range? Range represents the typical temperature that week. I don't know. The range represents how far apart the lowest and the highest measurements were that week. Is it for a week? I think it's in the temperatures for the daily high temperatures. 2, 3, 4, 5. It's 7. It's for a week. Okay. The range represents the amount of spread in the middle half of the data that week. I think, yeah. According to the ranges, which city's temperature were more varied in that week? According to the ranges. To the ranges, the temperatures more. To the ranges, the temperature, the same amounts of variability. Okay, the interquartile range. Calculate the IQR of temperatures. Okay, this 1, 2, 3, this is 4. We have 33 minus 25, we said 8. Okay, calculate the IQR. Okay, we got 27 minus 24, that's 3. What is the best interpretation of the IQR? The IQR represents the typical temperature that week. IQR represents how far apart the lowest and the highest measurements approximates the amount of spread on the middle half of the data that week. It could be A or C, huh? I don't know. I don't really present the typical temperature that week. Could it? Or I'd go with this one. According to the IQRs, which cities' temperatures were more varied in that week? 8 in R, which is varied more in Paradise, Miami. I don't think so. In Kansas City more. Okay, comparing range and IQR. On day to day. Well, we got right. We got an outlier here. So I think Kansas City has, I don't know, but we still get an outlier. Looking at the Dow, which seems to be more varied from day to day. Kansas City. Okay. Why might IQR be the preferred measure of spread in this context? The low outlier in the paradise temperatures has a large impact on the range of the data set, while IQR is not impacted by the outlier. I'll go with this one. Yeah, no? The data is more clustered in paradise. The IQR was larger in the Kansas City data, which reflects how the temperatures generally seem to vary more from day to day. Kansas City, they did in Paradise. Choose all answers that apply. Okay, article. Interquartile range. Interquartile range is the amount of spread in the middle 50% of the data of a data set. In other words, it is the distance between the first quartile and the third quartile. IQR. Here's how to find IQR. Put the data in order from least to greatest. Find the median. We know this. Example with an odd number of data points. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got this as a median. Then we got 4 here. So 3 plus 3 is 6 over 2 is 3. So we got 3 here. And here we got 6 and 4. That's 10 over 2, 5 minus 3 is 2. Okay. Which is the median. Okay. 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 Example with an even number of data points. 1, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So now they're fucking with me. 1, 2, 3, 5. I got 5. So this is the median. So what are we having? 5 here and 5 here. We got 1, 2, 3, 31.5, and 1, 2, 3, 26.5. So I got 31.5 minus 26.5. That's 5. So I would go with 5. You know how I okay. Median 29. What are you talking about? It's 5, yeah. Practice problem. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I got 1, 2, 3, 4, 5, 6. So this is the median. I got 5 here, 1, 2, 3, which is 6. And I got 3, I'd go 3. But seriously, 11. So the median is number 6. I'm left with 5, 5. Yep. Okay. Should we take this today? Measures of spread. Are we still in Unit 3? Ready for 12 minutes. Oh my god. Measures of spread, range, variance, and standard deviation. Don't we know the range, variance, and standard deviation? Okay.
In the last video, we talked about different ways to represent the central tendency, or the average of a data set. What we're going to do in this video is to expand that a little bit to understand how spread apart the data is as well. So let's just think about this a little bit. Let's say I have negative 10, 0, 10, 20, and 30. Let's say that's one data set right there. And let's say the other data set is 8, 9, 10, 11, and 12. Now, in both, let's calculate the arithmetic mean for both of these data sets. So let's calculate the mean.
Why are you doing this?
And when you go further on in statistics, you're going to dealing with samples of it, and you're going to try to estimate things for the entire population. So I don't want you to worry too much about that just now, but if you are going to go further in statistics, I just want to make that clarification. Entire population of our data. This is the entire population of our data. So we're going to be dealing with the population mean. We're going to be dealing with, as you see, the population measures of dispersion. I know these are all fancy words. In the future, you're not going to have all of the data. You're just going to have some samples of it, and you're going to try to estimate things for the entire population. So I don't want you to worry too much about that just now, but if you are going to go further in statistics, I just want to make that clarification. Now, the population mean, or the arithmetic mean of this data set right here, it is negative 10 plus 30 is 50 divided by 5.
Yep.
It's equal to 10. Now, so this is once again have the exact same arithmetic mean. When you average all these numbers and divide by 5, or when you take the sum of these numbers, this right here, this data set right here is R. And from that, you say the other data set is calculate the arithmetic mean for both of these, the mean. And when you go further on in statistics, you're going to understand the difference between a population and a sample. We're assuming that this is the entire population of our data. This is the entire population of our data. So we're going to be dealing with the population mean. We're going to be dealing with, as you see, the population measures of dispersion. I know these are all fancy words. In the future, you're not going to have all of the data. You're just going to have some samples of it. And you're going to, so that's 40, and worry about the word population or sample and all of that. They have these sets of and all of that. They have both of these data sets. They have the exact same population means. Or if you don't want to worry about the word population or sample and all of that, they have both of these data sets have the exact same arithmetic mean. When you average all these numbers and divide by 5, or when you take the sum of these numbers, divide by 5, you get 10. Some of these numbers to each other are very further away from 10. Even more disperse. More disperse, right? These one way, this is kind of the most, which is 30 in our example. And from that, you subtract the smallest number. So 30 minus negative 10, which is equal to 40, which tells us that the difference between the largest and the smallest number is 40. So we have a range of 40 for this data set. Here, the range is the largest number, 12, minus the smallest number, which is 8, which is equal to 4. So here, range is actually a pretty good measure of dispersion. We say, OK, both of these guys have a mean of 10. But when I look at the range, this guy has a much larger range. So that tells me this is a more dispersed set. But range is always not going to tell you the whole picture. You might have two data sets with the exact same range, where still, based on how things are bunched up, it could still have very different distributions of where the numbers lie. Now, the one that you'll see used most often is called the variance. The variance. Actually, you're going to see the standard deviation in this video. That's probably what's used most often, but it has a very close relationship to the variance. So the symbol for the variance, and we're going to deal with the population variance. Once again, we're assuming that this is all of the data for our whole population, that we're not just sampling, taking a subset of the data. So the variance, its symbol is literally this sigma, this Greek letter squared. That is the symbol for variance. And we'll see that the sigma letter actually is the symbol for standard deviation. And that is for a reason. But anyway, the definition of variance is you literally take each of these data points, find the difference between those data points and your mean, square them, and then take the average of those squares. I know that sounds very complicated, but when I actually calculate it, you're going to see it's not too bad. So remember, the mean here is 10. So I take the first data point. I say let me do it over here. Let me scroll down a little bit. So I take the first data point, negative 10. From that, I'm going to subtract our mean, and I'm going to square that. So I just found the difference from that first data point to the mean and squared it. And that's essentially to make it positive. Plus the second data point, 0 minus 10 minus the mean. This is the mean. This is that 10 right there, squared. Plus 10 minus 10 squared. That's the middle 10 right there. Plus 20 minus 10. That's the 20 squared. Plus 30 minus 10 squared. So this is the squared differences between each number and the mean. This is the mean. This is the mean right there. That is the mean. I'm finding the difference between every data point and the mean, squaring them, summing them up, and then dividing by that number of data points. I'm taking the average of these numbers, of the squared distances. So when you say it kind of verbally, it sounds very complicated, but you're just taking each number, how far, what's the difference between that, the mean, square it, take the average of those. So I have 1, 2, 3, 4, 5, divide by 5. So what is this going to be equal to? What is this going to be equal to? Negative 10 minus 10 is negative is plus 30 minus 10, which is is 1,000. It's equal to 1,000 of dispersing out. Maybe I could scroll up here. The variance of this less version there. And let's compare it to this data set over here. Let's compare it to the here. 8 minus 10, 2, 3, 4, 5, and is 1 or 5, which is equal to 2. So the variance here, let me make sure I got that right. Yes, we have 10 over 5. So the variance of this less dispersed data set is a lot smaller. The variance here, the variance of this data set right here is only 2. So that gave you a sense. That tells you, look, this is definitely a less dispersed data set than that there. Now, the problem with the variance is you're taking these numbers, you're taking the difference between them and the mean, then you're squaring it. It kind of gives you a bit of an arbitrary number. And if you're dealing with units, let's say if these are each, negative, well, let's say these are, let's say they're distances. So this is negative 10 meters, 0 meters, 10 meters, this is 8 meters, so on and so forth. Then when you square it, you get your variance in terms of meters squared. It's kind of an odd set of units. So what people like to do is talk in terms of standard deviation. Standard deviation. Standard deviation, which is just the square root of the variance. It's just the square root of the variance, or the square root of sigma squared. And the symbol for the standard deviation is just sigma. So now that we figured out the variance, very easy to figure out the standard deviation of both of these characters. The standard deviation of this first one up here, of this first data set, is going to be the square root of 200. Square root of 200 is what? The square root of 2 times 100. This is equal to 10 square roots of 2. That's that first data set. Now, the variance of the second data set is just going to be the square root of 2. Variance is going to be the square root of that. Sorry, the standard deviation of the second data set is just going to be the square root of its variance, which is 2, which is just 2. So the second data set has 1/10 the standard deviation as this first data set. This is 10 roots of 2. This is just the root of 2. So this is 10 times the standard deviation. 10 times the standard deviation. And this, hopefully, will make a little bit more sense. Let's think about it. This has 10 times more the standard deviation than this. And let's remember how we calculated. Variance, we just took the each data point, how far is away from the mean, squared that, took the average of them, times the standard deviation. Sense intuitively, right? I mean, they both have a 10 in how far is away 10 times. Look at the two data sets. This has 10 times the standard deviation. 10 times the standard deviation. Standard deviation. 9 is only 1 away from the 10. 0 is 10 away from the 10. 10 less. 8 is only 2 away. This guy's 20 away. So it's 10 times, on average, further away. So the standard deviation, at least in my sense, is giving a much better sense of how far away, on average, we are from the mean. Anyway, hopefully you found that useful.
Wait. What was that?
Guys, 9 is only 1 away from the 10. 0 is 10 away from the 10. 10 less. 8 is only 2 away. This guy's 20 away. So it's 10 times, on average, further away. So the standard deviation, at least in my sense, is giving a much better sense of how far away on. So let's look at the two data sets. This has 10 times the standard deviation. 10 times the standard deviation. Standard deviation. Which makes sense intuitively, right? I mean, they both have a 10 in here, but each of these guys, 9 is only 1 away from the 10. 0 is 10 away from the 10. 10 less. 8 is only 2 away. This guy's 20 away. So it's 10 times, on average, further away. So the standard deviation, at least in my sense, is giving a much better sense of how far away, on average, we are from the mean. Anyway, hopefully you found that useful.
Oh my God! What was I doing?
That first data set has 10. This has 10 times the standard deviation. 10 times the standard deviation. Standard deviation. Which makes sense intuitively, right? I mean, they both have a 10 in here, but each of these guys, 9 is only 1 away from the 10. 0 is 10 away from the 10. 10 less. 8 is only 2 away. This guy's 20 away. So it's 10 times, on average, further away. So the standard deviation, at least in my sense, is giving a much better sense of how far away.
Okay, variance of a population.
Let's say I'm trying to judge how many years of experience we have at the Khan Academy, or on average, how many years of experience we have. And in particular, the particular type of average we'll focus on is the arithmetic mean. So I go as an estimation of at Khan Academy. But let's say years of experience, experience. This is our population mean. Population point of, and I'm going to divide it all by the number of data points I have. Plus x2, plus x3, plus x4, plus x sub 5, subscript 5, all of that over 5. And as we said, this is a very fancy way of saying I'm going to sum up all of these things. I'm going to sum up all of these things and then divide by the number of things we have. So let's do that. Get the calculator out. So the population, how much spread there is around that mean, or how much do the data points vary around that mean? And obviously I can give someone all the data points, but instead I actually want to come up with a parameter that somehow represents very interesting. So the population plus 5, I really don't need a calculator for this, plus 7 plus 14. So that's 5 data points, and I'm going to divide by 5. And I get 6. Well, that's very parameter. And so what I do, the population variance, I'm going to variance from this number, give someone all the data points, but instead I actually want to come up with a parameter that somehow represents how much all of these things on average are varying from this number right here. Or maybe I will call that thing the variance. And so what I do, so the variance, and I will do, and this is a population variance that I'm talking about, just to be clear, it's a parameter. The population variance, I am going to denote with the Greek letter sigma, lowercase sigma, this is capital sigma, lowercase sigma squared. And I'm going to say, well, I'm going to take the distance from each of these points to the mean, and just so I get a positive value, I'm going to square it, and then I'm going to divide by subtract and my mean. And then to that, I'm going to add the squared distance between 3 and my mean. 3. And then I'm finding the difference between this. I have function right over here. If I square that, I get 9. 5, I get 5 plus 9 squared distance away from my population mean. So I squared each of these things. I liked it, population mean, and we denote what we did right over here. Well, let's just think it through. We're just saying that the population variance, we're taking the sum, the nth, take the item back to this thing, we're going to square it, so the way I've written it right now, this would just be the numerator. I've just taken the sum of each of these things, the sum of the difference between each data point and the population mean, and squared it. If I really want to get the way I figured out this variance right over here, I have to divide the whole thing by the number of data points we have. So this might seem very daunting and very intimidating, but all it says is take each of your data, figure it, take the number of a data population. I tend to make a lot of careless mistakes when I do things while I'm making divide from our population mean is equal to 20. You might say, wait, these things aren't 20 away. Remember, it's the squared distance away from my population mean. So I squared each of these things. I liked it because it made it positive, and we'll see later.
Wait, what? You see it later?
Later, it has other nice properties about it. Now, the last thing is, how can we represent this mathematically? We already saw.
Yep.
Let's say that you're curious about studying the dimensions of the in the polygon. So let's come up with some. I'll just get an arithmetic means the way is 6 squared, and then we're going to divide all of that. By plus what is a mildly interesting question. It's in meters. And so you might say, hey, that's kind of a weird unit if we're trying to figure out, if we're trying to visualize or think about how dispersed we are from symbols with just a sigma. Makes a lot of sense. And in this case, what's it going to be? It's going to be the square root of 316, and I get 0.56. I'll just round to the nearest thousandth, 0.562. So it's approximately 0.562 meters.
So you might be saying, Sal, what do we call this thing that we just did? The square root of the variance. And here we're in a new color. I'm using that yellow a little bit too much. Under this value, that's find variance. We could have taken things to the fourth power. We could have done other things. We could have not taken them to a power, but taken the absolute value here. The reason why we do it this way is it has neat statistical properties as we try to build on it. But that's the population standard deviation, which gives us the data is varying from the mean. It is a measure of how much the data is varying from the mean. In general, the larger this value, that means that the data is more varied from the population mean. The smaller, it's less varied. And these are all somewhat arbitrary. These are all somewhat arbitrary definitions of how we've defined variance. We could have taken things to the fourth power. We could have done other things. We could have not taken them to a power, but taken the absolute value here. The reason why we do it this way is it has neat statistical properties as we try to build on it. But that's the population standard deviation, which gives us nice units, meters. In the next video, we'll think about the sample standard deviation.
Okay. Introduction to standard deviation. Standard deviation measures the spread of a data distribution. The more spread out a data distribution is. Wait, let's see. Am I recording this? Oh my god. No. Introduction to standard deviation. Standard deviation measures the spread of a data distribution. The more spread out a data distribution is, the greater its standard deviation. The more spread out a data distribution is, the greater its standard deviation. For example, the blue distribution on bottom has a greater standard deviation than the green distribution on top. Okay, interestingly, standard deviation cannot be negative. A standard deviation close to zero indicates that the data points tend to be close to the mean, shown by a dotted line. The further the data are from the mean, the greater the standard deviation. Which of the data distribution below has a greater standard deviation? A. Okay, that's correct. Introduction, calculating step by step. Yep. Sigma x minus the mean square over n number of times. Sum of, yep, value of that z, mean of that z, of data points in the population. Since after we break it down in the common sections, we'll walk through a step by active. Find the mean, find each data point, sum. Now it takes an important note. The formula above is for finding the standard deviation of a population. You're dealing with a sample. You'll want to use a slightly If you are dealing with a sample, you will want to use a slightly different formula below, which uses n minus 1 instead of n. The point of this article, however, is to familiarize you with the process of computing standard deviation, which is basically the same no matter which formula you use. This is for a sample. Why are there two formulas? Step-by-step interactive example for calculating standard. First, we need a dataset to work with. Let's pick something small so we don't get overwhelmed by the number of data points. Here is a good one, 6231. Okay. Finding the mean. Finding the mean in mu, which is the mean. In this step, we find the mean, which is represented by the variable mu. Fill in the blank. Okay. I got 3, 3, 6, 6, 12 over 4. That's 3. 3. Okay. Finding x minus mu square in. Okay. In this step, we'll find, okay, 6 square, the square of the distance from the mean. Complete the thing. Right. Point is 6 and the mean is 3. So the distance between them is 3. Squaring this distance gives us 9. Oh, I'm gonna do all of this. Okay, so I got 2 minus 3. That's, well, that's a minus 1 square. That's 1. 3 minus 3, that's 0. So 0. This is the mean. Actually, this is the mean itself. So it's gonna be 0. Squared, it's gonna be 0. Okay, 1 minus 3, that's gonna be minus 2 squared. That's 4. Am I correct? Right. 1 minus 3. 1 minus 3, that's minus 2. Minus 2 squared, 4. Okay. Step finding sigma. Okay, we're gonna calculate this. 4, 1, that's 5, and 9, that's 14. 14. Okay. Over n, how many? 1, 2, 3, 4. Wait, data points. 1, 2, 3, 4. So I got 14 over 4. 14, 4. 3.5. I'm gonna take the square root of it. Okay, the square root. God damn it, it's 1.87. Nearest hundredth. Okay. We did it with successful summary of what we did. We broke down the formula into 5 steps. Find the mean, mu. Okay, I know what we did. Try it yourself. And here's this data set. I just did it myself. What do you mean? Standard deviation. Band. Okay. So now we're gonna get the mean. Should we? He wants the standard deviation all at once. Data points. At 1, 4, 7, 2, 6. Okay. Standard deviation. I gotta get the mu equal 1 plus 4 plus 7 plus 2 plus 6 over 1, 2, 3, 4, 5 over 5. Gonna get 5, 12, 14, and 6, that's 20 over 5. I got 4. So, and now I gotta do, wait, what am I gonna do? I'm gonna get, remember that? The sigma square, the variance, I'm gonna get the variance. So, which means I got 1 minus 4 square plus 4 minus 4 square plus 7 minus 4 square plus 2 minus 4 square plus 6 minus 4 square all over 5. So let's calculate this. God damn it. 1 minus 4. Wait. Let's do this. 1 minus 4 all squared. Oh my god. Plus 0 squared plus 7 minus 4 squared plus 2 minus 4 squared plus 6 minus 4 square. Okay, all over 5. Well, we got equal 26 over 5 equal over 5. It's going to be 5.2. So this is variance. Variance. Okay. SD, which is standard deviation. Again, I just take square root of 5.2. So square root of answer is going to be, well, it's going to be equal 130 over 5 equal 2.28. So let's check our answer. 2.28. All right. Do you want to do some exercises? Okay, should we practice, you guys? Following are numbers of lemons. Okay, I don't care. Find the standard deviation of this data set. So we got, oh god damn it. Hate this. Okay. Yep. I got 12, 14, 5, 13, 11. Okay, let's check this out. Get the mean equal 12 plus 14 plus 5 plus 13 plus 11 over 5. Right, I got 5. 1, 2, 3, 4, 5. So let's calculate this. 12 plus 14 plus 5 plus 13 plus 11 over 5. That's 11. So I got 11. 11. Do you want to do it his way? Okay, or that way? It's up to you. We could do it either ways. We could do standard deviation like this, Okay. Twelve minus 11, which is the mean, square, plus 14 minus 11 square, plus 5 minus 11 square, plus 13 minus 11 square, plus 11. Oh shit. Minus 11 square, all over 5. I got 5 data sets. So we're gonna do this. I got 12 minus 11 squared plus 14 minus 11 squared plus 5 minus 11 squared plus 13 minus 11 squared plus 11 minus 11 squared all over 5. I got 10, so it's gonna be equal the square root of 10 equal, so square root of 10, well, it's the square root of 10, but in terms of numbers it's gonna be 3.60 to the nearest hundredth. So 3.60. Yep, we could have done it here. Okay. So again, give me. Okay. Data sets. What are we having? 18, 16, 15, 15, 16. New 18 plus 16 plus 15 plus 15 plus 16 over 5. You know the 5 because it's there is 5 data points, data sets, data points 1, 2, 3, 4, 5. Don't confuse it because it's 5 every time. So anyways, 18, 16, 15, 15, 16 over 5. That's 16 actually. So we got SD equal 18 minus 16 squared plus 16 minus 16 squared plus 15 minus 16 squared plus 15 again minus 16 squared plus 16 minus 16 squared. Got 16 twice. All over 5. So let's get it into the calculator. Can we do it? What do you say? What are we having? Where's the fucking... Seriously. Where's the fucking... Oh my god. Oh, I'm not gonna do this. Sorry guys. Can't do that. It's a fucking waste of time. Okay. 18 minus 16 square plus 0 square plus 15 minus 16 square. Okay, do we need this? Yes, we need this. 15 minus 16 square. This is actually the easiest stuff I ever, because this is gonna be 0. You see this? This is 0. 16, so this is 0 and this is 0. And here is minus 1 square, which is 1 plus 1, and I got 18 minus 16. That's 2 squared, which is 4. So 4 plus 2, here I got 1 is 6. 6 over 5, I would say. 6 over 5. But I'm gonna check here. It's 5. Oh my god, it's 5. Seriously. What's happening? Something I did is wrong. Four. See, I forgot the plus sign here. Plus. Well, it's 6 over 5. 5. That's equal 1.2. You want to see it yourself? 6 over 5. No. Yep, it is 6 over 5. Equal 1.2. See it? So, 1.2 words. Okay. Okay, standard deviation of this. Let's do this. All here. I got 6 and 5, that's 11. 11 and 13. 11 plus 13 plus 8. Okay. Okay. And then, wait, what happened? What happened? Okay. And then I got 32 over 4. That's 8. So I got the standard deviation. I got the mean, which is the mu 8. So I got, now, gotta use brackets. 6 minus, what did we say, 8? Yep, 8. 8. That's squared. That's squared. Plus 5 minus 8 squared. You get 13 plus 13 minus 8 and close the brackets, squared. I got 38. I don't need the last one because it's going to be 0. 8 minus 8 is 0. Squared is 0 still. So I got 38 over 5. Nope. Yeah. I got 38 over 4. Sorry, 4. That's 9.5. So this is the variance, and we need the square root of 9.5. That's 3 3.02, and we're gonna go with that 3.02. So 3.02. Oh my god. Okay. Again, well, 3, 5, 9, and 7. That's 16 over 4. 4. So I got the mu is 4. So I got 3 minus 4 is minus 1 squared is 1 and 2. So I got 1 and I got plus sign. I got 2 minus 4 is minus 2 and squared is 4 and I got plus sign. I got 4. Wait, why is this 3 minus, what are we having? 4. It's minus 1 here. Yeah. Square. So I got 4 minus 4 is 0. We don't need that. I got 7 minus 4 is 3. 3. Wait, 7 minus 4 is 3. 3 squared is 9. So I got 9. Wait. Nope. 9 is 14. So I got 14 over 4. I got the square root of 3.5, 1.87. 1.87. Oh yeah. Hells yeah. Well, you guys, this is gonna be it for today's statistics and probability. See you later.